think we're ready to start. I just need a quick check from online people. I literally just started. So if you're online and if you can hear me okay, can you just please write in the chat, like, sounds great? Probably super low. Maybe, is that better? All right, if you can hear me in the chat, please just write, sounds okay, too quiet, too loud. I can adjust it a little bit more from here. All right, I got some sounds greats, so that's good. Okay, thank you very much, everybody. Sorry for the little bit of a late start. The doors were locked. If you're online, the doors were locked when we showed up. So the 15 minutes I saved to get things set up is kind of carved down to about 5 minutes, which wasn't quite enough. But I think we're here, and we're here now, and we're ready to get going. So what I've done is I've compiled all of the questions that people have submitted to me, and I have them available kind of just on as a PDF here, and I can go through and just address them. I was seeing a lot of very common, like similar types of questions. A lot of people were struggling with the like, what type of isomers are these two molecules? A lot of people weren't super confident with the like E1, E2, SN1, SN2, and how to distinguish. Some people had asked about potential energy diagrams, how to draw mechanisms. There was some carbon-13 NMR stuff. There's a couple of questions on that. So I hope this group of questions that I have is somewhat representative of all of the questions that people had. And in my mind, too, I think representative of what is going to be on the midterm, at least for my section. I will say as well that this is being recorded automatically. It's going to be available online anytime afterwards. And to get to it, all you have to do is follow the same link that I already sent out. The same link for the online people that brought you here where you are now will also bring you back to the recording later on. And it's already posted on Acorn, so it's available really anytime. Not that there's a whole lot of time between now and the midterm, but there it is. I can give you a bit more detail as well on the structure of the midterm. It's similar for both sections, and I know it has 9 questions. Some questions are worth 10 points, most of them are. 2 of them are worth 15. They're just worth a little bit more. I'd say it's roughly similar in length to the first midterm, depending on how quick you are, right? I think there was some stuff on the first midterm. The second midterm, depends how fast you are, right? Hopefully time isn't too much of a factor. I'm still personally feeling out, like usually I don't give 50-minute exams. So, you know, I'm doing my best with that as well. I'm also, like, if you want to show up to the midterm for my 8:30 midterm a little early, that's okay too. So I'm probably going to be there a quarter after. And if you want a little bit of extra time, you can come then. Yeah, should I jump right in? All right, perfect. I got a question online. Is it possible to share the PDF with what we're going over tonight? Yes, I absolutely can do that. But the PDF literally is just questions that are plucked from old exams, assignments, midterms, and things like that. All right, so let's get going. This first question is a carbon-13 NMR question. And I'm going to actually move my computer up here. Hopefully people can still see me okay. The reason I'm doing this is just so for the online people, I'm not getting this weird view of my shoulder or something. Yeah, that was good. Okay, so this first question is a carbon-13 NMR question. And what it's asking for is how many peaks you would expect to see in the carbon-13 NMR spectrum. And I can tell you that there is a carbon-13 NMR question on the midterm as well. And what you have to be able to do is predict 2 things. One, looking at the symmetry of the molecule, understanding how many peaks to expect total. And number 2, based on sort of the hybridization of the carbons, where roughly you expect to find them in the spectrum. So this first one, what really we're looking for here is symmetry within the molecule. And with this particular molecule, there exists a plane of symmetry which runs right through there. And that plane of symmetry, that carbon that it's intersected is actually, it's an sp3 carbon, it's tetrahedral. So actually those two methyls are not in the same plane as the rest of the molecule, they're 90 degrees. But there's a mirror plane that makes those two methyls equal. That was kind of weird. A and A. There's B, which is the one that goes through. And then there's C and there's C. Those are mirror images of each other. And so this molecule, you'd expect to have a total of 3 peaks. And those 3 peaks are all going to be kind of in the sp3 region, probably not that far off of 20 parts per million. That's upfield, that's to the right side of the NMR spectrum. Probably between 15 and 30 is where you'll find all of these peaks, because there's no electronegative atoms and everything's sp3. The one next to it, you may agree with me that there is a mirror plane that runs up the molecule like that, which makes the left and the right mirror images of each other. So those two, those are both A. Those are A and A. This is B and B, and C and C. Then you have D and D, E, E, F, F. So each of those is a unique signal. You expect a total of 6 signals here. The first 3, A, B, C, are sp2 hybridized carbons. And so what that means is those 3 peaks will all show up somewhere between around 120 to 130, 140 maybe parts per million. D is a carbonyl carbon, and carbonyl carbons that are part of an ester, like you see here, around 170 to 180. And the other 2, E and F, are sp3s, so you see those somewhere between probably 0 and 60, with E being closer to 60 and F being closer to 0. And E is closer to 60 because it's attached directly to an oxygen, which is electronegative. So that kind of gives you what you'd expect for that structure. The third one, by the way, that's not number of peaks. There's 3 peaks. 2 is sort of like this is number 2. Number 3 here has no symmetry. I mean, it's got a plane of symmetry that cuts all of the molecules in half in the same plane as that flat benzene ring, but that doesn't reflect any carbons onto any other carbons. So there's really nothing here to draw for symmetry planes. So what we can do is just label them A, B, C, D, E, F, G, H. And each one of those is going to be a unique carbon. So that's what, 6, 7, 8 peaks total. And of those, A is a CH3, that's an sp3 carbon. That's going to be up around 20 or 30. H is also an sp3 carbon, but bonded to an oxygen, so closer to maybe 60. And then the other 6 are all going to be in the sort of 120 to 130 or 140 range. There is a table on the midterm on the last page, which has sort of the rough ranges where you expect to find the different kinds of carbons. Just in case you were wondering. I think I got a question about that in Friday's class. So that has been added to the midterm, so it's available. This next one has a plane of symmetry that runs up the molecule like that. So we have A, which is the CH3, B, CC, D, D, E. Okay, so this one has a total of 5. A would be in the sp3 region. The other 4 would be in the sp2 region. The next one has A, B, C, D, E. Each one of those carbons is unique because there's no symmetry. And you get 5. They're all sp3. C and D attached to oxygen, so they're closer to 60. The others closer up to, say, 20. This next one, though, does have a plane of symmetry. And this one might be a little bit hard to see because the way it's drawn, it doesn't appear that there is any symmetry there. But remember, generally speaking, single bonds are able to rotate. And so because they're able to rotate, what that means is you can turn that bond around there, which will turn the molecule into this shape. So if you can rotate bonds and make planes of symmetry, do it, because that will cause those to be equivalent then. Now we have a plane of symmetry, and why don't we go A, B, B, C, C, a total of 3 signals here, all sp3s. Next, we have this compound here. It's an ester that's part of a ring. Those are called lactones. If you count the carbons, there's no symmetry in this molecule that makes any carbons equivalent, so everyone is unique. So we have A, B, C, D, E for a total of 5. And next, this last one, and this might be hard to see, but there is a plane of symmetry which goes through there. And you might look at that and say, well, that's not a plane of symmetry. You have that cyanide, the nitrile group pointing down, and there's nothing up. But again, I don't need a software update. Not right now, at least. That bond can rotate around, and that one that's hanging down, you can just put it straight up, and then there is a mirror plane that goes through there. And what that does is it causes, let's go with light blue, that and that to be the same, that and that to be the same, C, D, and E. And don't forget E. E is one that sometimes people miss because there's a C in a nitrile. It's part of that carbon-nitrogen triple bond. So that's everything here. 1, 2, 3, 4, 5. Cool. Everyone okay with that? Will we get a table on this midterm? Yes, we will. So maybe what I'll do after this is I'll post exactly the table on midterm that you guys will get. You can Google them. It's like one of the first top 10 hits on Google. Carbon-13 Nmr correlation chart, I think it's called. There's some that are extremely complex and detailed with like dozens and dozens of different ranges. Mine's pretty basic. There's like maybe 6 or so different ranges that are indicated, and that's it. So yeah, that will be available. It's attached on the last page of the midterm, and you guys will have access to that. All right. Next question. Flumethrin is an insecticide used to protect livestock against ticks and fleas. Its structure is shown below. And the question just says, how many chiral centers are there in flumethrin? And the way this structure is drawn, there's no dashed or wedged bonds anywhere. And we're probably used to like looking for the dashed and wedged bonds to indicate the chiral centers. So if that's all you look for, you might just pick 0. But there are chiral centers here, whether or not we're indicating exactly whether there are arrests with those dashed and wedged bonds. So what we're looking for here is how many carbons are there that have 4 different groups attached to it. And you know, there's lots of ways to do this. You can just look at every carbon. Right away, if a carbon has a double bond, it cannot be a chiral center. So almost like what you can do is like, you know, go through all these ones that have double bonds. None of these are possibilities. Certainly not a triple bond. Same here. Like, you know, all these ones get X'd out, and you're only left with a couple others. Now, those CH3s are not chiral centers because it's got 3 of the things the same. The carbon that's attached to them is also not a chiral center because it's got 2 methyls. If it has 2 things the same, it cannot be a chiral center. So really what we're left with is this one, and this one. And it turns out all 3 of those are chiral centers. And just check and see what's attached. Don't forget the hydrogens that are attached but not drawn in. So 3, I guess, is the answer here, which is D. Okay. Fischer projections. I got a lot of questions about Fischer projections, and there's a couple that made it onto this chart here. And once we get through this whole list as well, like I'm very happy to take other questions, or go back if people want me to go back, or anything along those lines, just to make sure that that's, you know, that that's possible. It is funny too, because some of the questions I got, I like found mistakes that was like on a midterm back in 2011, and it's like for 10 years it's been posted, and it's been never found until this year, so I don't know why. But this particular question has a mistake. Pentate diol is not a real thing. It's pentane diol. What that molecule is, pentane means that there's 5 carbons, and 2,3 diol looks like this, because it goes 1, 2, 3, 4, 5. And each one of those is a chiral center, carbon 2 and carbon 3. So there are 4 different possible isomers of this molecule. You could have RR, RS, SR, and SS. And this question is asking us to draw Fischer projections of all stereoisomers. Okay, so this isn't too bad. Here's what we're going to do. We're going to draw 4 Fischer projection things here. Like that. And then what we're going to do is indicate, you know, carbon 1 is the top one, 2, 3, 4. Now, there's also a carbon 5. So what we're going to do is just draw in a carbon 5 just at some angle like that. So that bottom one is the bottom methyl. And then those horizontal lines will have an OH on one end and also a hydrogen, because this molecule has hydrogens here that we don't draw in when we draw bond line structures. Okay, so here's how we do. H, H, OH, OH, H, OH, OH, H, HOH, HOH, and what's the other combination? OH down here and OH up there. I didn't leave myself very good spacing there, but those are the 4 possibilities. It's like both to the right, both to the left, left, right, and right, left are our options here. Now, one thing I do want to point out, and this is kind of a small point, but it's a little pet peeve that I see every single year. You see how I draw, when they're on the right side, I drew them as OH, and when they're on the left side, I drew them as HO. That's because it's the oxygen that's bonded to the carbon. So when that line comes over, it should point to the oxygen, not to the hydrogen. So if I see a bond like this, it drives me crazy. Because the hydrogen is on the other side, right? We're trying to draw it at least somewhat realistic to how this thing actually looks. Cool. So then it wants to know what else. Absolute stereochemistries. So what we need to do here is identify each of these chiral centers as being RRS. Okay, that's not so bad. Let's go to the first one, and we're going to look at carbon 2. And the first thing we need to do is rank the priority of all of the groups attached to the chiral center on carbon 2. And so what we get is top rank goes to oxygen, bottom rank goes to hydrogen. The other 2 are carbon groups, and the bottom going down has higher priority than the CH3 because it has a carbon and an oxygen attached. The lowest priority carbon you can get is a CH3. Okay, so we ignore the low group, which is the hydrogen. We look at the other ones. 1, 2, 3 goes around. That's clockwise. Yeah, I'm trying to think of how a clock goes, but that's clockwise. And so normally clockwise means R, but in this case, because the hydrogen's horizontal, that means it's coming towards us. So that center is actually S. So we have an S there. And this is the way you think about it. When OH is to the right, it's S. So the next one is also S. And then the next one has to be R because it's not to the right. And the last one has to be R as well. So you really only got to do it once, and then you know the whole row. The next one, and I'm going to do the next one on the next structure just because the other one's already messy. I'm going to use green this time. So we're looking at carbon 3. That's a chiral center. Top priority is the oxygen. Bottom is the hydrogen. And then we have up top, this gets second priority. And then this gets third priority, is the ethyl group down below. So now if we go 1, 2, 3, that's clockwise again. The hydrogen is still horizontal. So clockwise in this case actually is counterclockwise, so it's actually S. So when OH is to the left, it's S. So that's S. When it's to the right, it must be R, and that one's R. This has got a lot in it, doesn't it? It wants more than that. It wants us to indicate the two that are enantiomers. There's another error. Enantiomers. It's enantiomers. No, there's only one T in there. And two that are diastereomers. So enantiomers are chiral molecules that are mirror images of each other. So those two are mirror images of each other. And also, these two are mirror images of each other. So there's two pairs of enantiomers here. When you have a chiral molecule and you have an enantiomer of it, for the enantiomer, every chiral center must flip. So the left one, that's SR, in the flipped one, it's RS. And the one that's SS, which is this one, its enantiomer is RR. So all centers flip. So I'm going to call this enantiomer. And it also wants two that are diastereomers. Diastereomers are a pair of molecules, like if there's two chiral centers, one flips, but they both don't flip. So that would be like these two. In this case, the top one stays the same. They're both R. Bottom one changes. You could also think of these as cis-trans, a cis-trans pair, because the two OHs are on the same side, so you could say that they're cis, and here they're on opposite sides, so you could say that they're trans. And looking for cis-trans pairs is another way of rapidly identifying diastereomers. Go with this one. Wonderful. Now this comes from the first question in chapter 6. And in chapter 6, what this says is draw the structure of possible products in the following reaction and suggest the name of the most plausible mechanism. So this involves using that table that I used it in class several times. It's on our Instagram account. You've seen it, hopefully, before. If you haven't, your life's about to change for the better, because really it takes the guesswork out of questions like this. That table is not provided to you, though. That's a table that you have to know. You have to know, should understand as well the principles behind how that table was generated. But this one, what you do is you first of all classify the alkyl halide as methyl primary, secondary, or tertiary, where in this case it's going to be primary. The way you do that is you look at the carbon with the leaving group, which we call the alpha carbon, and you count how many carbons are attached to it, which we call beta carbons. So this is only one beta carbon, so it's primary. And then you look at the conditions, and we broke the conditions up into 4 different classes. There was a bulky alkoxide, which is a negatively charged, has an O-, and bulky means that the carbon attached is a tertiary carbon. So this one is a bulky alkoxide. The second one is a small alkoxide, so the same thing, but if it was a primary. Then there was a strong nucleophile, which are usually negatively charged nucleophiles. And then the last one was none of the above, but a polar product solvent. So this falls into that first category, bulky alkoxide. And this threw a lot of people the way it's drawn here, because it shows the alkoxide second. It shows the alcohol with it. It's 2 things there. and there's heat. And we have a category for product solvents. People might look at that and say, well, there's a product solvent and there's an alkoxide. What do I do here? And the answer is, if there's anything there that has a negative charge, ignore everything else. That's going to be the one that's the most reactive. It's going to force the action. It's going to make the reaction go a specific way. The reason why they're both listed is because that other thing, the potassium salt, that alkoxide is a solid. And you can't do a reaction in a solid matrix. You need a solvent. And so the solvent here is just the first one. Whatever the alkoxide structure is, we always use the same alcohol as the solvent. So they're together as a pair. You can't really have one without the other. And so they're both written that way. So what this would suggest, a bulky alkoxide with primary would give you as a major reaction E2. For now, I'd like you to just ignore the minor side. And the reason for that is when this year we've only focused on the major products of reactions like this. There will be a minor product, which is an SN2. Okay, there can be some substitution, but for this midterm, for sure, all we're looking for is the major product, the primary one. So I'm just going to put a big X through here. So then we have an E2 reaction, and what I'm going to do here is a little more than just draw this out. I'm going to actually draw the mechanism, and I'm going to draw the potential energy diagram for this reaction. Okay, so let's draw it out here. We have how many carbons? 1, 2, 3, 4, 5, Br. We have our alpha, and we have our beta. And our beta has 2 hydrogens there and there. Why don't we put some dots on the bromine? And we have our bulky alkoxide. So let's bring in our bulky alkoxide. First thing we do is get rid of the K+. If there's ever a potassium, lithium, or sodium, wash it away. It's not going to participate in this reaction. Just the anion. It's a strong base, and it's looking for those juicy beta hydrogens to pluck off and force this reaction forward. All right, so it's got 2 betas. Let's switch to blue. It's going to pick off one of those hydrogens. At the same time, that CH bond breaks, the electrons goes to make the alkene. And as well, the carbon-bromine bond will break, and those electrons go to the bromine. So what that will create is that. Be very careful when you do these to count your carbons before and after. These reactions will all preserve the number of carbons. Just make sure it's very easy, especially when you have a long chain like this, to either add a carbon or lose one. Just make sure you have the right number. You have a bromide as well. And you have now your alkoxide became an alcohol. So this only has one step. So what does the potential energy diagram look like? Well, you have starting material, and you have product. One hump, because the mechanism has one step. The very top is the transition state. No intermediates. You only have intermediates if there's 2 or more steps. What's the rate determining step? The step. Right? There's only one step, so that's the rate determining step 2. Potential energy diagram here is pretty straightforward. Sometimes what we like to ask is transition states. We showed transition states in the slides for E2 and SN2. So if I was to draw a transition state, that's sort of like what this top part is representing here in the potential energy diagram. And really, it's sort of like the halfway point between starting materials and products. So it would look sort of like this. You'd have kind of half your double bond formed. That hydrogen is half broken. That bond is half formed. And the bromine is like half gone. Something like that. The transition state is nice to be able to sketch because it kind of shows you a little bit what bonds are stretching or forming during that particular step. But that's about everything I could ask you about this particular question. And I could ask you any part of it. I could say, like, you know, what's the mechanism, first of all? Second, what's the product? Third, what's the mechanism? And last, what's the potential energy diagram? Or what's the transition state? All of those things are included in this answer here. Is the mechanism chart posted on Acorn for both sections? I think the mechanism chart is, it must be one of the PowerPoints, but maybe what I can do and should do and will do is just post it as a separate thing. In fact, what I can do is just post just a huge image on the top of our Acorn page with that chart. That should be helpful. All right, here's the next question. It's almost the same question. It's just the only difference here is we still have, you know, like a primary alkyl halide. This one is just a small alkoxide. This is the business end of what's going on here. Ethanol is our solvent. We don't really care. There's heat here, and there's the alkoxide. So our chart, what we predict here is because this is a small alkoxide, not only is it a strong base, but it's also a strong nucleophile. And primary alkyl halides love doing SN2s. They'll do SN2s under any situation unless there's a bulky alkoxide. So SN2, this has SN2 written all over it. And just by changing the structure of the alkoxide, you're sort of switching the direction of the reaction from E2 to SN2. All right, so let's draw this. So our alkoxide, remember, we make it negatively charged. Potassium's gone. Potassium doesn't do anything here. And now what we have to do is, again, SN2 is just one step. Single attack. It attacks the back side of the alpha carbon. Since the alpha, it comes in like that. Bromide comes off. And we have 1, 2, 3, 4. 1, 2, 3, 4 carbons. And O ethyl. The oxygen is what attacks, knocks out the bromide, and that's it. That's our SN2. Count all your carbons, count all your atoms before and after. Make sure you didn't lose anything, especially with these long chains, right? There's 4 carbons before and there's 4 carbons after. We've added O ethyl, so it's acting as a nucleophile in this example. Potential energy diagram, starting material, transition state, product. Single step, you know, this is our rate determining step. This is our activation energy. Of course, it's the rate determining step. It's the only step. SN2s usually come with inversion, but this doesn't have a chiral center where the reaction's happening, so we don't have to worry about it here. Last thing is the transition state. I'm going to draw it like this. Let's just draw it the same as before, I guess. No. I want you gone here. I don't want the whole chain gone. So in the rate determining step, the bromine is sort of like partly broken. The nucleophile is partly coming in. And then you have kind of like a hydrogen here and a hydrogen here. So at that moment in time, there's kind of 5 things kind of attached to that carbon. We're not really exceeding its octet though, because you only have kind of like partial bonds. And so if you count half bonds, we're still kind of at the octet. So yeah, that's the transition state. Sometimes we put brackets around it and put something like that. That little double dagger thing indicates that it's a transition state. Great. Everyone doing great so far? Here's another one. This is primary still. And now we have KCN with heat and DMF. KCN, remember, we get rid of the potassium. What we really have is cyanide, CN minus, strong nucleophile. It's one of our strongest nucleophiles that we use. The structure of that looks like a carbon triple bond nitrogen, lone pairs on each, and the negative charges on the carbon end. And it's going to do, what do you think here? Yeah, this one's an SN2. Primaries love SN2s. We've got a really strong nucleophile. We've got a polar A product solvent, which are best for SN2s. It's kind of got everything going for it. All right, so the mechanism, I guess, it's going to look a lot like the previous one. It's just that. And our product looks like that. And that's kind of it. That one good? Transition state will look the same as the previous step. The potential energy diagram, same as the previous one. They're all going to be pretty much similar. All right. Next one. There's kind of 2 in 1 here. We have the same molecule starting out, tertiary here and tertiary here. The difference here is one has just a polar product solvent. Let's call that a PPS, polar product solvent, and that's all. And there's heat where, you know, if you're going to make, if you're going to do, so in this situation with a polar product solvent and tertiary, generally you'll get a mix of SN1 and E1, where heat usually gives you a higher percentage of the E1. And so sort of a simplification that I would recommend is if there's heat, do E1. If there's no heat, do SN1. So we're going to do the E1 here. Probably why there's 2 here is one's E1 and one's SN1. Because even with heat, there's still going to be a mix. But we'll just draw the E1. We won't worry about the minor because heat is on there. The other one, when you add the alkoxide, that changes things entirely. Right? The alkoxide likes to force the action. It's not going to wait around for a sluggish old SN1 reaction. It's not going to wait for a carbocation to form. And so what this one's going to do is E2. Kind of think of SN2 and E2 as sort of like active reactions, violent reactions. And if you have a good nucleophile or a good strong base, it forces those E2 SN2s. But just this, you know, ethanol doesn't do too much. It'll wait around, make carbocations, give you E1, SN1. So let's draw out the E1 for that. That will come off. E1 is what we're drawing here. That makes a carbocation. That is our alpha. We have our beta, and our beta. All kinds of beta hydrogens here. It's expected because it's tertiary. Doesn't matter which one of these that we take. You take any one that you like. And we are, what are we doing here? Oh yeah, we need to remove a beta hydrogen and we need a base to do that. We don't have a strong base, but we do have a polar product solvent, which is ethanol. Looks like that. Pick any hydrogen that you like to remove. Use purple for this one. Let's go for that one. The pair of electrons in the CH bond come down here to make a double bond. And you get that product. Is that product E or Z? Or neither? not E, not Z, neither. Why is it neither? Well, it's neither because one end of the carbon has two of the things the same. So that's it. If you flip it, it's the same molecule back and forth. That's what you look for, EZ, neither. Neither means one end of one carbon has two of the same groups. It's a little trick question to throw in there. Okay, let's say I asked you to put a potential energy diagram for this reaction. How would that look? This is a little trickier than E2 or SN2 because there's two steps and the relative size of the humps is important now. So this will look like this. You have your starting material. Well, I'm not going to actually, I didn't do that very well. I'm going to draw it like that. So if this is like A, your carbocation is B, and your product is C, this is A, B, and then C is down here. Carbocation, so what you need to show here is, first of all, two steps. So there's like one intermediate here. That's an intermediate, INT, intermediate, which is this carbocation B. So you need two humps. There needs to be two transition states, here and here. And the first step must have a much higher activation energy than the second step, because that's the rate determining step. Forming the carbocation, rate determining step. B should be much higher up in energy than A or C, because B is a carbocation. They're much less stable than a carbon that has all four bonds. So that would be what I would be looking for a potential energy diagram for the E1. Okay, I kind of skipped out here on the E2. I drew the E2 mechanism above. It's the same mechanism as before, same potential energy diagram as before. Basically, every time you draw an SN2, it should have the same, every time you draw an E2, it should have the same, same mechanism, same potential energy diagram, same transition states, again and again and again. Just, you might change a bromine for a iodine or something like that. But it's the same basic thing again and again. Just to confirm, will we ever be expected to draw the major and minor products on the midterm? That's a no. Okay? This midterm has no questions with major and minor products. Good. Except maybe one exception. I just said no major minor products. This isn't actually an exception to that rule, so that rule holds. Sometimes you have two major products, and I'll show you what I mean when I say that. Okay, the next example, we have a chiral molecule. Look, we're adding a chiral center into the mix here. Secondary, alkyl halide. And in the first example, we have a very strong nucleophile. I tell you what the mechanism is, SN2. The other one is ethanol heat. I guess we're going to say there's E1 is probably major here, but I'm indicating right in the question that I want SN2, SN1, both SN1 products. So here's an example with two products, but it's not major minor. They're both major. They're both actually formed in exactly equal amounts. So here's what I mean. The first one is SN2. The nucleophile here, remember, you get rid of the sodium, CH3S-. It's going to be a nucleophile. It's going to attack the carbon with the bromine. It's going to attack the chiral center, and it's going to invert the stereochemistry. That's what SN2 does. So in the product, you'd want to draw it like this, SCH3. Remember, the atom with the negative charge is the sulfur. That's the atom that's going to be attached to the molecule after, and the CH3 comes with it. In the other example, we're using ethanol and heat. What happens here is, because we have SN1, we lose the leaving group. We have our carbocation here, and that carbocation is planar. It's flat. Okay? The top and the bottom are identical. It's not chiral anymore. It's lost its chirality as soon as it loses the leaving group. And there's no preference if an ethanol comes over. It's going to act as a nucleophile. It can attack, you can kind of think of it as in the front or the back. Like it can attack either side of that flat carbocation. It's like a sheet of paper. The top and the bottom are the same. There's no preference for one way or the other. And what you're going to end up getting is this. It's going to come in front. And in back. Now, we don't like final products with charges, so we need another step here. We need to remove that last H+. And to do that, we can just take like another methanol, CH3OH. Methanol can do lots of things. It can be a nucleophile. It can be a base. It can be an acid too. It's going to remove that H+. And what that becomes, that line I made somehow. Well, let's get rid of it. Okay. OCH3, 2 dots there. You could do the same thing to the other one. And let's make this one pink. And this is going to make, it's going to get a little more crowded here, but. So those are the two products. You know, this one is what, S, this one's R. And you're going to get a 50-50 mix. You're going to get a racemic mixture. Exactly. So this was my exception of drawing more than one product. It's technically, they're both major products because they're formed exactly in equal amounts. So both of them together are kind of the major product. The reason it's racemic is because that carbocation is perfectly flat, no preference to come in from one direction or the other. It's just statistical. I see two questions, so I'll get the back question first. Yes, so that was a very good question. If you have an SN1 reaction, the question was, for people online, do you always get a racemic mixture when you do SN1? I'll say yes for the purposes of this course. Okay, there are examples, and I'll show you one actually. This is a very kind of like, I'm not going to like give you something like this on a midterm, but there's a molecule that looks like this. Okay, and I think if you, this is a close relative. So this weekend, we put our Christmas tree up, decorated for Christmas. It's an artificial tree, so it's not going to dry out. But real Christmas trees produce a chemical called pinene, which has a structure very similar to this, which is the pine smell you get from a Christmas tree. And you can buy it if you have an artificial tree, or like me, go into our chemical storage room and get pure alpha pinene. And anyway, it has that kind of double ring structure. And so what happens with this, you could lose bromine. You can make a flat carbocation, but the top here, because there's hydrogens, the top and the bottom aren't quite the same. So you don't quite get a racemic mixture here, but I'm not going to give you weird examples like this. Every example you will see from me on the midterm or the final, SN1 will produce a racemic mixture. SN2 always will just invert whatever you have. So you'll only get a racemic mixture from SN2 if you started with a racemic mixture. It'll just give you back whatever you started with. Okay, are we ready to give a break to some some of these reactions for a bit. We'll come back if people want to see more of it. That's totally fine. I got a question on classifying alkenes where we talked about alkenes. They could be, this is the beginning of Unit 7, they could be mono-substituted, di-substituted, and di came in 3 flavors, cis, trans, and gem, or geminal. It's tri-substituted and tetra-substituted. So really what we're asking here is, look at the double bond, count how many carbons are attached to those 2 sp2 carbons, and that'll tell you what class you have. So this first one, this is the first sp2 and the second sp2. There's a total of 2 carbons attached, 1, 2. So this is going to be di-substituted. So if it's di, you have to say which type of di, cis, trans, or geminal. Cis is when the 2 carbons are on the same side of the double bond, and that kind of makes a bowl shape, like you see here. This is like 1, 2. This would be a cis di. It kind of looks like a bowl, upside down here, but still a bowl. A bowl that's ready to go in the dishwasher. The other one, if it's trans di, it looks like a zigzag. And so this one is a trans di. And the third possibility is gem di, and that's when both carbons are on the same side of the double bond, same end of the double bond. So that's this example here. This third one, we have 2 carbons. We have 2 groups attached, so it's a di. When the 2 groups are on the same carbon, we call them geminal. So that's a gem di. All right, this next one here, look at the double bond, look at the 2 sp2s and count how many carbons. Get 1, 2, 3. So this is just a tri-substituted alkene. This one, 2 sp2 carbons, we have 1, 2, 3, 4. So this is a tetra. And down here, we just have a mono. Those 2 carbons, there's just 1 carbon attached. And the next one, what do you think the next one is? It's di, yep. And what kind of di? Gem di. Great. So that's it. And I guess you need to know the rank here of stability. Where most stable is tetra, which is better than tri. Then you have trans di, which is better than cis di, and gem di, which are both the same, which is better than mono. And I guess you have an unsubstituted as well. But there's only one unsubstituted alkene, and it's ethene. And we're only looking at carbons. So we don't really use this categorization if there's like a chlorine or a fluorine or an oxygen or something like that. You'll only be ever asked this question by looking at carbons. By the reverse argument, often my midterms will have a question like draw an example of. And if I say draw an example of a trans di-substituted alkene, don't draw, please, something like this. I mean, it's not wrong, and I know what you're getting at, and probably at this stage I'd just give you full points, but when I say these di-substituted, tri, tetra, whatever, use carbons in a question like this. It just gets a little messy when you have non-carbons because other stuff can happen for these that you'll learn about in Organic 2. Like, for example, if you have an OH, these kinds of molecules actually aren't stable. Usually, there are some examples that are stable, but usually they will spontaneously convert into molecules like this. It's a process called tautomerization, which you'll learn in next semester. All right, rewinding all the way back into Unit 4. This one says, draw the most stable chair conformation of 1,1-dimethylethyl cyclohexane, also known as T-butyl cyclohexane. So that's this molecule, T-butyl cyclohexane. What we've taken to doing in recent years is actually giving you a template for the cyclohexane chair to start from. And that's, I think, because of so many years of really terrible renditions of chairs, which makes it really hard for us to grade because we don't know exactly what you're trying to show. If you use our templates, we know if you got it or don't have it. So that's what a cyclohexane chair roughly looks like. It's not perfect, but it's good enough. And right away, if you're going to have to draw, I guess we want the most stable chair conformation. This is going to have two conformations. No. It's going to have a mirror image. It's going to have another one. So pick any carbon you want. I usually like to pick the end carbon. And we have a T-butyl, and we also have a hydrogen there. Could look like that, or you could ring flip it, or like that. This question, I think, only asked for one. It asked for the more stable one. So this one is, and this one's more stable because the big bulky T-butyl group is, in this case, going to be in an equatorial position and not axial. All right, part B. Draw the two stereoisomers for 1,4-dimethyl-cyclohexane bond line drawings and draw the most stable chair conformation for each. So 1,4-dimethyl looks like that. And it wants it both stereoisomers. So we need to indicate the stereochemistry. Because these are sp3 carbons, they'll have 3 dimensions. And so what we can do is use wedges to draw one. And we'll use the dashed line for the other one. What's the relationship between these two? Yeah, these are diastereomers because the first one is cis, and the second one is trans. What about this one? That's cis. Is that what's the relationship between the first one and the third one? These are the same. They're not enantiomers because enantiomers need to have chiral centers, or need to be chiral molecules. And this molecule is not chiral because it has a plane of symmetry there. Has no chiral centers. Not a chiral molecule. Plane of symmetry inside makes it achiral. So these two are the same thing. It's like you took the molecule, the first molecule, and just flipped it over upside down without rotating or moving or changing any bonds at all. Anyway, I'm getting beyond what the question's asking for. It says draw the most stable chair conformation for each. So what I'm going to do is delete the stuff I don't need. That. And we are going to do the first one, the cis. And so this is the way I'd recommend this. If you see a wedged bond on the bond line structure, label it up. And if it's hashed, used down. Okay. And so what we're going to do is draw our cyclohexane chair there. That, not great, but you know what I'm getting at here. These are mirror images of each other. And that's carbon 1, carbon 4. Each of those two carbons are going to have two bonds that look like that. And I'm going to call this one up and down, up and down. And now we're just going to go to the molecule and just copy. Up in both cases are CH3s. Up is CH3. The down are the hydrogens that aren't drawn in. Well, now they're drawn in. And that's it. I'm going to try that one again over here a little bit. Okay, so carbon 1 is still here, carbon 4 is there. And when you flip it, carbon 1 is still up, still CH3, and on carbon 4, the CH3 is still up, hydrogen down there. One thing yes, sorry, I'll take your question. You don't have to draw the hydrogens in, no. And one thing I'm going to say as well is what sometimes people love to do is start out by drawing their cyclohexane chair and then putting all these bonds in, right? A lot of people like to start there. I think I drew one of them wrong, that one. You can do that, but if you left it like that, every one of those lines that you drew is a methyl. And usually that's not, I don't give you molecules like that. If you want to leave them there and they're just hydrogens, you have to draw the hydrogen in. Otherwise, if you just leave it, it's a carbon. I read it as a CH3, and that's incorrect. So just make sure that when you get to that point, every one of your lines has something on the end of it. If it doesn't, I assume it's a CH3, because that's how bond line structures work. Generally speaking, it's cleaner if you just don't draw them at all. Like, this structure will get a lot messier if I went in and drew all the extra hydrogens, the other, 8 hydrogens. If they're not necessary, I like the hydrogens at the carbons where there's something else besides hydrogen. It just makes it even clearer. Yes. No, I think I'd have to tell you. Because there's 2 possibilities here. Because this one says draw the 2 stereoisomers, which we've drawn, 1 and 2, and draw the most stable chair conformation for each. So we're only dealing with the first one now. But after we do the first one, we'll deal with the second one next. And that said, let's deal with the second one now. So what we can do is draw exact same thing as before. And we're going to, this is going to be carbon 1 and carbon 2 over here. Sorry, carbon 1 and carbon 4. Carbon 1 is up, and so if we go to carbon 1, we'll put the CH3 up and the hydrogen down. Carbon 4 is over here. It's got 2 groups. The CH3 here is down, and the hydrogen is up. Once again, I'm going to erase my second one and redraw it. So after it flips, carbon 1 has an up and a down, and carbon 2 has a down and an up. So of these 2, this one is more stable because it has 2 equatorial groups. The other one has 2 axials. The other one's way worse. The previous one, they're both equal in energy because you have 1 axial and 1 equatorial in both flipped forms. You could make one more stable if they weren't both methyls. Like if one was T-butyl and one was methyl, the T-butyl wants to be equatorial more than the methyl does because it's bigger. So then they wouldn't be the same. But I think in this case, I do have a question here. If SN1 has the 3rd step of making sure the product isn't positive, should the energy diagram include that 3rd step? And the answer there is yes. So I'm going to go back to that example, which probably everyone's forgotten about by now. I didn't see that question before. So this was this reaction where there's 3 steps. If I do them horizontally, looks like this. Dimethyl, and then so this has this extra step. That comes over, that comes over. So what this would look like, this is 3 steps, 1, 2, 3. The first step has the biggest energy to make a carbocation, and then it goes downhill to make the cation, and then there's another small energy gap here. So that third step is to take that H plus off. Apologies for answering that later than question. Yes?
Would you include that last step if you say we have an S&P?
Yes. So do you want to see an example?
No, I'm okay.
Okay. Okay, perfect. Yes. No. So yeah, the question was, do we include on the potential energy diagrams, like, do I care if this is endothermic or exothermic? You know, if it's delta H is positive or negative? I don't care. They're all going to be like kind of close. What I care about for the energies is the carbocation's got to be much higher than the starting material in the product. Whether the product's a little higher than the starting material or vice versa, I don't really care. Yeah, it'd be kind of hard to predict in a lot of cases. Yeah. Usually, I think eliminations are endothermic, and depends on the base though, right? If you have a really strong base, they're not endothermic. So there's a lot of detail that goes into determining that we don't care about too much. Great. I was asked this one. RRS. This is just, identifying a chiral center here and what it is. So this one shouldn't be too bad. We have a chiral center here. This is an amino acid. What's it called? Methionine, I think it's called. Anyway, we have also not drawn is a hydrogen, which automatically is going to get rank 4. We have a carbon, and a nitrogen. So the nitrogen outranks carbon, higher atomic number. So that's 1, that's 4. And then we have to compare the other 2 against each other. So that carbon is bonded to a sulfur and 2 hydrogens, while that carbon is bonded to 3 oxygens. Double bond counts as just oxygen, oxygen, and the third one is also oxygen. The top one wins because you look at the first element first. If there's a tie, you go to the second element. If there's a tie, you go to the third. We have sulfur versus oxygen in the first row, and sulfur has a higher atomic number. Therefore, this group is ranked 2, and this group is ranked 3. So now if you go 1, 2, 3, goes around that way, which means S. Cool. People good with R and S generally? Okay. This question was put forward. Which of the following solutions would be optically active? So what optically active means is that it rotates the plane of polarized light. If you have a solution that has a chiral molecule, a pure chiral molecule, it'll be optically active. If you have a solution that has maybe an excess of one chiral molecule versus its enantiomer, we call that an enantiomeric excess, that will also be optically active. If you have a racemic mixture, which is a 50-50 mix of a chiral molecule and it's enantiomer, that will be optically inactive, right? It has chiral molecules, but because it's 50-50, the light won't get rotated. Because one will rotate it one way and the other will rotate it the opposite way to the same magnitude, and they just cancel. So this says a 50-50 mix of R2-bromopentane and S2-bromopentane, that's racemic. So that's not optically active. A racemic mixture of ibuprofen and enantiomers is also not optically active, 50-50 mix again. A 2% structure of acetyl-acetone, structure in question 9. So this was obviously like a different exam or test or assignment or something where that structure was already given to you. I wouldn't expect you to know what acetyl-acetone is, but it has this structure like that. That molecule has no chiral centers. So if it's achiral, it will also be not optically active. So you need chiral molecules in there. The last one says a 5% mixture of R-glycine, an amino acid, in water. This turns out to be an error. This is the right answer. You don't have to know what glycine is. If it's a chiral molecule and that's all you have in there, doesn't matter what percentage the mixture it is, it's going to be optically active. When I say it's an error, the reason it's an error is in the real world, glycine actually is not chiral. It's the only amino acid that isn't. So it's like a super unlucky choice. Like just pick any other amino acid and it would be totally correct. The last one's a 50-50 mixture of water and ethanol, neither of which are polar. That's not going to be optically active either. So what you're looking for is the solution that has a chiral molecule in excess. So I could put an F here as well, like a 60% R2-chlorobutane and 40% S2-chlorobutane. That is optically active, because the enantiomeric excess is 20%, which is the major minus the minor. 60 minus 40 is 20%. So if you have some enantiomeric excess, you're going to have an optically active solution as well. Fischer projections. For the following Fischer projection of 2,3-difluorobutanoic acid, which of the 5 answers best describes the stereochemistry? So what we got to do here is identify R and S for both chiral centers. Let's zoom in on it. We'll use pink to do chiral center number 2. And we're going to rank our different groups. Fluorine gets top rank. Hydrogen gets bottom rank. And next we have carbon versus carbon. So that carbon is bonded to oxygen, oxygen, oxygen. Whereas that carbon is bonded to fluorine, carbon going downwards, and hydrogen. That means the bottom carbon here gets rank 2. This one rank 3 because fluorine, higher atomic number than oxygen. So then you go 1, 2, 3, goes around clockwise, which is R, but the hydrogen is on a horizontal position. So it's the opposite of that. It's going to be S. So this is going to be 2S, which right away we can cross off A and B. You can cross off meso, because meso requires there to be a mirror plane in the molecule. This is no mirror plane. So now we've got to do carbon 3 to see whether it's C or D. You can't just say the first one was to the right and was S, therefore the second one is also S. Can't do that. You have to do it all over again for the second carbon. So let's erase everything here. This time we'll go with purple, and now we're looking at that carbon. Number 1 is fluorine, number 4 is hydrogen, number 3 is methyl, and number 2 is the carbon up there. 1, 2, 3 goes around counterclockwise, but the hydrogen again is in a horizontal position, which means it's towards us. So we have to go the other way around, which is R. So this becomes 2s, 3r, which is C. These ones are good. Like, the problem with RNS questions is, like, if you have no idea at all what to do, you got a 50-50 chance anyway, right? And so if I give you 2 of them and have now 4 answers, you only have a 1 in 4 chance because you got to guess 2 in a row right to get the question right. So anyway, can't be too nice. Okay, so now we got a bunch of these guys, a lot of them. I will say a lot of these ones are going to be much tougher than the ones you can expect to get on the midterms, especially the ones where I did kind of like mixed media, you know, like the ones where, like, well, this one's a chair and this one's a bond line, or this one's a Newman projection and this one's that, you know. I don't think there's anything like that on this midterm. I think all of the ones, a couple of them on the midterm, but they're both bond line or they're both whatever, you know. So those are a little more straightforward. We can do some of these though if people want. See some yeses and some nos. I was specifically asked for these ones. Maybe I won't do every one of them, but I can do a few. That first one, number 25, has a chiral center. It has no mirror plane in the molecule. And so these 2 structures are chiral and they're mirror images. If you think of like a mirror on top. Another way to think of enantiomers is if you have a chiral center and you take any 2 groups on the chiral center and swap them, then those are enantiomers as well. So this kind of think of as like atom 1, atom 2, we've swapped them, and so that makes a pair of enantiomers here. The next one looks kind of the same, except we've lost our double bond. And as a result of losing our double bond, we actually lost our chiral center. Because now, those 2 sides of that ring are identical in either direction. There's not 4 different things anymore on that carbon. So it's not chiral. So enantiomers is out of the question. These are the same thing, just flipped upside down. Picked up the molecule and you flipped it over, and now we have the same thing all over again. Actually, the next one is too. If you pick that molecule up and flip it over, the oxygen's going to point down. It's going to flip that part upside down. But also the double bond will kind of come around the other side. Okay, so these are the same ones too. Now in these 2, the position of the double bond has changed. So these are constitutional. Constitutional isomers are the easiest ones to see. They're like fundamentally different in like which atoms have which bonds. Okay. The next one, it's kind of a jerk move, isn't it? This one. You can reorient this. It turns out that these 2 are the same. I can see it just by reorienting it in my head, the way they look. That's probably not easy for a lot of people. An easier way to do this maybe is if you decide there is a chiral center in this molecule, assign RNS to those chiral centers. If they're both R, then they're the same. If one's R, one's S, then they're different. Then they're enantiomers in that case. Move past that one. This one's number 30. This one is a Newman projection. What I probably recommend with these is converting the Newman projection back to a regular structure, which in this case, 1, 2, 3 carbons. Just that. And this is the same thing. You've just looked at a different conformation. You've rotated a bond. That's all you've done. So, you know, one's staggered, one's eclipsed, but that's the same molecule. You didn't move anything or break any bonds or do anything like that. No chiral centers, no enantiomers to deal with or anything like that. I realize some of these ones were like quite difficult, right? Yes.
2 questions.
Mm-hmm.
So the dash and wedge lines don't really for these.
That's a loaded statement. So the statement was the dash and wedged lines don't mean anything. For which one? Number 30 or number 29?
For like 29, 28, all those. Because you can sort of like not rearrange them, but
Right. So the question is, what's really the meaning of the dash and wedge bonds in an example like 29?
yeah.
So you mean the left structure or the right structure? Or both?
Both,
Okay. So what this means in the first structure, remember that carbon here is tetrahedral, or it's roughly tetrahedral at least. It's not perfect 109.5s because of the 3-atom ring. It's like 60 there, but it's... So what that means, if you think of the ring as being flat, then the 3-membered ring is like 90 degrees to it.
Yeah, I just meant like when comparing them together, whether one has like a dashed line doesn't.
So if I drew it the other way around, if I drew it like that, and I kind of cheated on that, didn't I, there? These two are opposite. Those are like, one it's like this, and the other it's like that. So those would be enantiomers of each other.
Okay.
Yeah. Yeah. Does that make more sense? You said you had 2 questions.
Yeah. The second one was because I'm looking at 29, like the 2 and 29.
Yeah.
And if you like turn the like second one there, the double bond would be on like the opposite side.
Depends how you turn it. You could turn it that way, but if you did that, the oxygen would be pointing backwards.
Okay.
Yeah. Question on line 2. So if you move a double bond to a different place in a molecule, it's a constitutional isomer, not a diastereomer. Yes-ish. So yeah, if you have like a double bond there, and then now you have a double bond here, you move the double bond, those are constitutional isomers. If you have an example like this, and you move the double bond over there, those are the same molecule. So there's not constitutional isomers because it's just the same molecule flipped around. So that question that I got, if you move a double bond to a different place, is it a constitutional isomer? Well, yes, but it depends how it's drawn. Okay, and this part is probably the most confusing part for most people, identifying these two, because really what it comes down to is visualizing exactly in your head, in 3 dimensions, really an abstract shape, right? And you're learning a new language even of how we're identifying that shape. Like you could probably see a 2-dimensional picture of a 3-dimensional object like a house and understand the 3-dimensionality of it with things like shading, you know, but we don't use shading because shading is hard to do. We use dashed and wedge bonds, which are kind of indicating the 3D shape. And once you get used to it, you can probably look at these structures and rotate them around and compare them more easily than you can now. Yeah. Doesn't matter at all because it's on carbon 1. It's not a chiral center. It's really like these Newman projections are used to show conformations. So typically you have multiples that are the exact same molecule. You're just rotating through a bond. That's really why we use them. And we'll use them again in Unit 7. Yes?
Could you show it with the example of the projection of the
Yeah. So I could come up with an example. Got some space here. That one and that are enantiomers. They're mirror images. That front carbon is a chiral center because it has 4 different groups attached. It's got the CH2, CH3. A side-on view of this one Like if your eye was here and you were looking at that molecule down that line, it would look like Br here, CH3, hydrogen, ethyl, like that. So you have a chiral center, and that could be R or S. Those are tough to see. We haven't done a lot of examples like that. So the likelihood of finding one of those on this midterm isn't high. We skipped a few. Fischer Projections. These two, we have, I guess you can think of this one as cis and this one as trans. So that would make these two diastereomers. This one is chiral here. This one's meso. Now this next one, they're both cis. So they're not diastereomers. They look like mirror images, so they could be enantiomers, but in order to be enantiomers, they also have to be chiral. And these aren't chiral because they're meso, just like the previous one. So that means these are the same thing. It's almost like you took the first one. Actually, if you drew the first one and then flipped your paper upside down, you have the second one. So yeah, you didn't move anything. You didn't touch any bonds. So yeah, those are going to be the same molecule. This one's a pain. All right, well, if you number this chain from one end, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The other one, we're going to start on this side. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the first thing we're going to check is to see if they're constitutional isomers. They both have a methyl on carbon 3. They both have 2 methyls on carbon 4. And they both have a methyl on carbon 7. So they're not constitutional isomers. So what we're going to do is check the stereochemistry at carbons 3 and 7. We're going to see if they are R or S. So let's start with this one. Let's put our hydrogen there. This is going to get 4. The big long chain is 1. The ethyl is 2, and the methyl is 3. Doing the priorities here pretty quick at this point. 1, 2, 3 goes clockwise, but the hydrogen is forwards, not backwards, so it's counterclockwise. So that's S. And if you go to the other structure on carbon 3, we have the priority going 4, 1, 2, 3. It's going around that way. The hydrogen's in front, so it's the other way. It's S. So far we have the same molecule. It's all going to come down to what happens at carbon 7, where we have 4. That's going to be 3. We have a 3-carbon chain or a much longer chain with branches. That's going to be 1, and that's going to be 2. So 1, 2, 3 makes that center R. And if we do the same thing over here, we have 1, 2, 3, 4. 1, 2, 3 is S, but it's flipped because the hydrogen's in front. So that's R as well. Same. Okay, the chiral centers are the same in both. The connectivity is the same in both. That's going to be same molecule over again. Sound good? This one is a fun one. Look at that. That's how you draw a 10-carbon ring. Because it's just neater than if you do like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But I didn't quite make it neat, but it starts to look like a sphere or like a circle and kind of messy. So yeah, this is a nice clean way to do it. This has an alkene in it that's cis, and this has an alkene in it that's trans. What do we call cis-trans pairs? Diastereomers. So yeah, these are diastereomers. And we have these ones as well. I think the same one was up there, right? Those are cis-trans pairs as well, diastereomers. Which of the following molecules is chiral? Not A, because it has a mirror plane. What do we call A? Meso, yep. E is also meso, mirror plane through there. D doesn't have, well, it has a mirror plane right through the middle of the molecule, so it's not chiral, no chiral centers. B does not have a mirror plane. B is chiral. And C doesn't look chiral at the moment. It doesn't look like it has a mirror plane at the moment. But it does, because to see mirror planes in linear molecules like this, all of the carbons need to be eclipsed. So if you rotate that around to make it eclipsed, you got that. Mirror plane, meso. So yeah, the answer is B. I just realized I have your pencil. It's like you can't leave early, can you? Well, you can. I can just bring you your pencil tomorrow, but if you wanted it later. Okay, if you got to go, just tell me and I'll steal someone else's pencil. Another mechanism question. The ones that give people the hardest time, I think, are the questions where you have like a neutral thing attacking, because then you have that extra bonus step where you have to make the... So this is methyl bromide plus acetic acid. The question says, draw a complete mechanism for formation of the major product. Show all lone pairs, blah, blah, blah. This is what kind of an alkyl halide? Primary, methyl, secondary, tertiary. Methyl, good. And polar product solvent, right? PPS, that means it's SN2. Methyls are always SN2. It's the only option. You can't do eliminations with one carbon. You can't make carbocations with a methyl. So SN2 is what we got. It's also completely unhindered, so it's a fast reaction. So we have, I'm going to draw out our molecule like this. CH3Br. You have two oxygens with lone pairs that could potentially each act as nucleophiles. I don't get too fussy over which one you use. I think the right one to use is the one with no hydrogen on it. That makes CH3 Br minus attached to oxygen. Like that. The reason it's better to use that oxygen is because that molecule there has a resonance structure, which makes it more stable, makes it easier to form. That resonance structure looks like this. Resonance structures, if they exist, stabilize things by spreading charge out. And so if you attack with the OH, you don't get those resonance structures. And therefore, you get a much less stable intermediate. But that's what you get. But we're not done because we have a positive charge now on our compound. What I like to do is actually draw the bond to hydrogen here. And we need to remove that extra hydrogen with some sort of base. And please don't use bromide as your base. It's the world's worst base. Iodide is a little bit worse, but bromide's a close second. As weird as it sounds, acetic acid is a better base than bromide is. Not by much, actually. This isn't great either. But anyway, we can use it. We can remove H+. I'm going to get rid of those things here. That's gone too. That goes there. And what we get is as our product. And the byproduct is like OH plus And that's a pretty hot acid. Like that's going to be a strong acid for sure. If it was water, it'd be like completely dissociating. But yeah, that's how you get your product here. I saw this hand first.
If we had used like the H at the very beginning instead of the 1O, would you have that wrong?
No, that's kind of a fine point. Like you have to use the oxygen. You have to start at a lone pair. But which oxygen you start with, I don't really care. It's technically correct to use the carbonyl oxygen, but yeah, that's based on the fact that you can get a more stable thing. Cares? No. So not for me at least. I don't know what you might have learned in the other section. I don't really care. Like if you didn't draw the bromide in here, I don't care. If you didn't draw, no, that's product. If you didn't draw this thing, I don't care. I just want the organic part to be in every step. And some non-organic chemists don't like the fact that we will often draw reactions that aren't balanced. Like we drop things and we'll pull in a solvent when we need it, and those sorts of things can upset people, but we do it anyway. All right, good? All right. Ooh, another one. For the following reactions, draw a complete mechanism. So what kind of alkyl halide is this? Good, secondary. Small alkoxide, big, what do we got? Small alkoxide, what's the mechanism? E2. Great. So honestly, that's half the battle. Like being able to look at the conditions and identifying right away what the reaction is going to be, huge step. So E2, this is where everything happens at once. We have our alpha, our beta, and our beta. This is carefully designed, so each beta is identical. We have our base here. We don't care about the neutral thing. It's just the solvent. And we remove the K plus so that we have CH3O minus. Doing the business here. It will remove one of the beta hydrogens there. Bromide goes. It wants all the lone pairs, so let's put them on the bromine. And that will give us double bond goes there. We'll draw the extra stuff. It's not needed. I think I put an extra dot there. It's gone now. Makes a molecule of methanol and gives you your product. So this kind of reaction is favored at high temperatures because this reaction has a positive delta S, because we begin with 2 particles and end up with 3 particles. Those types of reactions are entropically favored, and entropy at higher temperatures makes the reaction have a more negative delta G. Makes it more downhill in energy. All right. Oof, we got to the end. Questions from the floor time. Is there anything? Yes, I see a question up here.
Okay. There's a bunch of questions on the old versions. They're like, what conditions would allow for that? Could we go through like one example of how you would go about that? Like,
Absolutely. That's it.
It says like to take place in high yield.
Yes. So basically, you have to fill in the conditions to cause that reaction to give that as a major product. That's an excellent question to practice given what's on your midterm tomorrow. Okay? So this also gives you a little bit of leeway. Like there's often with these questions, there's several correct answers. So if I gave you something like I put like dot, 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 dot. You have to put in the conditions. And you have CN, like that. What you'd have to do is look at that reaction. You'd have to identify that there's been a substitution. If it was elimination, there would be an alkene. But this is a substitution. And there's been a chiral center that's inverted. So that should scream to you SN2. All that, right? So what conditions would give this SN2? Well, SN2s love strong nucleophiles, and the nucleophile has to be cyanide to give you that product. So let's put in our strong nucleophile, NaCN, or KCN or LICN, doesn't matter. You want negative nucleophile. It's nice to put the solvent in. Usually I don't really care if you don't put the solvent in here, but why don't we do the full meal deal and add the solvent and pick a good solvent. What's a good solvent for SN2? DMSO. Let's do DMSO. Perfect. Ideal. All right, let's give you a little bit of a tougher one. Did I add a carbon? I added a carbon. There. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, what mechanism is this? Well, first of all, elimination or substitution. Yeah, it's elimination. Do you think it's E1 or E2? It's got to be E2 and not E1. Why not E1? Right. E1 has a carbocation. You can't make a primary carbocation. So E1's off the table. It's E2. So we have a primary alkyl halide doing E2. What conditions would provide this reaction? Yeah, a big bulky alkoxide. So why don't we pick one? Let's, for the sake of completeness, add a solvent, which is the same alcohol as the alkoxide. That would do that reaction. If you picked a small alkoxide, I'd probably give you half points. Because small alkoxide might give you some of that, but the major would be SN2. Right? So that's the part of the question where it says to produce it in high yield. Right? To produce it in high yield means it's got to be the major product. You want to see more examples like this? Okay, what if I gave you something like, I feel like I haven't been using iodine much lately. So that means 50%, 50%, right? Starting out with a chiral molecule, it's all S, and we're throwing it away. We get S and R, 50-50 racemic. We've lost our chiral center. Well, it's there. It's just 50-50 now. What reaction do you think this is? Yeah, SN1. How do we know? Well, we know it's substitution because we didn't make an alkene. We know it's SN1 because we lost our chiral center. If it was SN2, we would have inverted it, right? Which we didn't do. It's SN1. What was our nucleophile here then? If it was SN1. Water, yeah. H2O. Would you add heat? Probably not, because that would give you elimination. So yeah, just water. That's all I'd want to see here, really. Not hydroxide, right? Hydroxide is a problem. It's a base and a nucleophile. It could give you E2. It could give you SN2 with a secondary like this. Let's see one more. What should the next one be? Yes. Yeah, so I'll give you an example like that. So that one's elimination. We don't know if it's E1 or E2. Both will give the same product. So a bulky alkoxide would do it. That would be correct. A small alkoxide would too. Or a polar product solvent and heat. That would give it to you too. This one would have tons of right answers. The only wrong answer, I don't know, like sodium chloride would be wrong. I don't know. Yeah.
Would you say it was E1 though because it is formed with carbocation faster? So that would be the reaction.
It all depends on the conditions. Because tertiary can form carbocations really well. You're right. The thing is, though, if you have a really strong base, like here, it can form a carbocation, but it can also react with the base quickly, too. And it turns out, if you do have like a really strong alkoxide like this, that's going to be faster than forming a carbocation. So any one of these reactions could work. I would probably avoid this one myself if I was doing the reaction, because you're probably going to get a significant amount of SN12, where the other ones will only give you elimination. But there's ways around, yeah, it's just, that comes down to this major minor thing. This should be, but I'd accept any one of those three as a correct answer in that case. So what you'll see eventually, especially on the final, you'll see questions like this with with questions and there's a blank, and you either have to fill in the conditions or the product or the reactant. And those ones I think maybe are even the toughest. Sometimes, it depends. Like sometimes they can be pretty straightforward. Like if I gave you like that, you look at the conditions, you look at the molecule, substitution happened, we have a strong nucleophile in an SN2 solvent, probably had an SN2, we have a pure chiral product, there's probably an inversion. So what we'll need here is something with a leaving group, like pick a leaving group, bromine, whatever, and you'd have to have the leaving group in the right place, and you have to indicate that there must have been an inversion by having the opposite stereochemistry in the starting material. So yeah, these reactions, I really mean it when you need to know these mechanisms forwards and backwards. Because like literally, you could get the questions forwards and backwards. But once you got them, like, I feel like this thing, these reactions, it's like, when you first learn them, it's a horrible mess of conditions and directions and major, minor. And then once like you kind of got them all reined in, it's like just a snap. You know what, you know, and it's not that hard. The trick is getting, of course, over that barrier to get to that point. But when you get to that point, actually writing these tests can be very satisfying because it's like you just do it. You know you're right, and it's not that tricky. Whereas those like enantiomers, same, those ones are always tricky, I find. Like, I can do them. I've done thousands of them before, so like I don't find them that difficult for me, but I still have to think about it, and it's not just obvious, if you know what I mean. They do take some thinking and can be tricky. Cool. Anything anyone else would like to see? Yes.
Can you do a mechanism with strong acid like H2SO4?
Yes.
Unless we're not going to see it, then
So in my section, I haven't seen the other sections test, but in my section, the reactions of alcohols is not going to be covered. I can do one. No. I think the other section, I think you guys got the same messaging, right? Maybe? No reactions of alcohols? Who's in the other section? Just a few people. Yeah. You guys too. So, I mean, we covered that in class, but I think the stopping point was the beginning of chapter 7 where we had E and Z, but no, yeah, you know what I mean. You guys did cover the, yeah, elimination and substitution, or just elimination? Yeah. Cool. Yeah. So I don't know, I haven't seen your midterm, but I have seen mine, and there's no reactions of alcohols on it. But actually, the reactions of alcohols are way easier than the reactions of alkyl halides. It's like no competition. The same thing happens every time. Pretty well. Anybody still with me online have questions? No, still have 26 people online. I'm happy. Oh, I see a question over here. Right. So I guess this is the question was for people online too. In some of the old midterms and the solutions, heat is shown for E2 reactions as well. It's not, so it's correct in the sense that yes, heat will help E2 reactions just like it'll help E1 reactions. But generally speaking, E2 reactions don't have competition in the same way. So it's not wrong to put it, but I don't really expect it either, if you know what I mean. It's kind of like writing the solvent. Like, it's nice to write it, it's nice to write heat, but if there's a situation where there's substitution and elimination competing, in those situations you'd want to add heat if you want elimination, if that makes sense. I don't know if I answered that question very well, but it's required if it's SN1 versus E1. It's not required in any other case. Yes, question over here. I think there's some multiple choice. I think there's maybe one, I don't know if it's a 10-pointer or 15-pointer, but yeah, there is some multiple choice going to be on there for sure. Yeah. Not as much though. It's the first one probably. Yes. Sure. Yeah, those ones. So if you're comparing leaving groups, iodide is always the best, followed by bromide, followed by chloride, and fluoride is awful as a leaving group, is not a leaving group in fact. If you see fluoride in there, it's a trick question. Nothing's going to happen if fluoride is there as the leaving group. In terms of nucleophile strength, for halogens, we talked about it a little bit. We said that in water or in a polar product solvent, iodide is the best, followed by bromide, followed by chloride, and fluoride is the worst in water. But in a polar A product solvent, like DMSO, DMF, acetone, whatever, it's the other way around. Fluoride is better than chloride, better than bromide, is better than iodide. Yeah, so there's an Instagram post with all of the solvents that you'll see, and there's also an Instagram post about all of the nucleophiles that you'll see as well, classifying them as strong and weak, and it has this thing in there as well. So polar product solvents, things like water, alcohols, and carboxylic acids. Whereas a polar A product solvent, we had like 5 or so that we used. Dimethylformamide, dimethyl sulfoxide, acetone, acetonitrile. That might have been it. There's a few others that you might use, but we haven't, like HMPA is another one that I don't know if we've ever used that, but yeah, there's some that we use. This is my favorite solvent, by the way, acetonitrile. It's got everything going for it. Mixes with water. It's doesn't absorb light, which is important to me as a photochemist. And low boiling point, evaporates off easily, cheap, non-toxic. Everything you could want in a solvent is acetonitrile. Solves everything. Yes, question. What's photochemistry? So it's like when you do reactions in the lab, mostly you add heat to get over the activation barrier, and you make your products. With photochemistry, you don't use heat, you use light. And often the actual reaction that happens is a completely unrelated path. So you can get products that you can't get using thermal chemistry. So it's all like, you know, things like photosynthesis are photochemical reactions. There's a whole lot, like vitamin D, when you go out in the sun, is a photochemical reaction in your skin that produces that vitamin. And it's interesting when you get down into the nuts and bolts of why light is different from heat. But you can definitely get reactions that won't happen unless you use light to make it happen. And so it's kind of my specialization. And there's a lot of interest in it for things like medicine and making materials and things like that, because if the reaction only occurs with light, because we have, you know, lasers that you can turn on and off, you can control when and where the reaction happens. So an example might be like chemotherapy. If you have cancer, you take chemo and it just goes through your whole body and it kills all rapidly dividing cells. So your hair falls out and, you know, you get very sick. You hope that it kills the tumor faster than the rest of you, but the whole idea is kill all dividing cells and, you know, hope you survive, right? Where, like, if you could, say, photochemically react something, so if you took a chemical that wasn't activated until it received light, then you could give somebody the drug and not have it activated until you shine a laser on that one spot. So you could activate it locally, you know. And so there's research going into stuff like that. And you can time reactions, so you can make the reaction start and stop when you want. And there's interest in doing that for biological reasons. And they study, you know, in biology, for example, like if you injected a chemical into an organism and it caused some effect, then you just watch it. It starts right away, and then as the chemical decomposes or whatever, the effect just slows down. With light, you could like start and stop. You could like, you know what I mean? You could start it and make the reaction instantly begin, and then you could give it another flash of light, and there's a lot of very interesting techniques around that kind of stuff. So, yeah, it's cool stuff. Yes.
There's a question in one of the, I don't know, it's probably this year, but it was talking about like, I think it had to do with like this concept here, and it was talking about like the solvation shell.
Yes.
So can you explain a little bit more about that?
Yes, the question was to explain what I mean about solvation shell, and what that really means is if you're in a polar product solvent, polar product solvents can do hydrogen bonding, which is very, very strong intermolecular forces. And if you get something like a fluoride ion, you know, it's round, you can get water molecules effectively hydrogen bond to it. So it's surrounded by these positive ends of the water molecules, and that really stabilizes the fluoride in water. But those waters are like stuck to it, and they're stuck to it hard. And so we call this like a solvation shell. It's a solvent shell around the fluorine of waters. So it's almost like, imagine you are trying to run a marathon and there's like 10 toddlers clinging to your arms and legs. that's like the water is clinging to the fluoride ion here. And they're clinging so tight, and the fluoride can't shake them, that it slows it down. It makes it a really bad nucleophile because it can't really get in and attack a carbon anymore because it's got this shell of waters around it. So it's not just it floating around, it's it and its entourage of waters. And so it's a kind of a big clunky thing going around. Now fluoride sticks really well because it's small and it has very concentrated charge. Iodide, on the other hand, like think of it like this. You know, there's still waters out here, but the charge is so spread out that the waters don't stick very well. And so it can kind of move and the waters just, you know, leave. So iodide is a good leaving group in water because the water doesn't slow it down much. But fluoride's really bad because it has that solvent shell surrounding it. That's why all of these nucleophiles are better in a polar A product solvent because they don't hydrogen bond to the ions. They don't slow them down. And so fluoride's the best there because it's small and fast and speedy and doesn't have any waters or anything else stuck to it. So it can react, it can get into tight places, and strong nucleophile for that reason. But it's the worst nucleophile if you're in water because of the solvent shell. Cool. I know everyone's like reluctant to leave because that one gem I just might say, like question 1 is about, no. Yeah, it shouldn't be too, it should be familiar, I think. Like it's the same types of questions as previous midterms. I mean, it's probably too late for me. Probably the best thing you can do at this point is go home and get a lot of sleep. So you want to be fresh. All right. So thanks, everybody. And thanks, everyone online, too. Good luck.